Voila. Wonderful. Thank you very, very much. If I talk at this level, can you hear me in the back okay? A little bit? Okay, I'll speak up. I have some slides here that have a lot of information. So there's a Google short link up there. If you want to download the slides and have them on your laptop, it's probably a good reference. How many people here have used Apache Spark before? Some? Okay, great. I mean, just to give you a preview, this is going to be fairly introductory material. This is meant to cover the essentials of introduction to programming in Apache Spark, but within 45 minutes. So it's going to be a very fast-paced, very introductory level. But at the end, I'm going to show some more sophisticated parts. I'll show a little bit of some practical applications of machine learning, graph analytics, et cetera. So first part, very intro, and last part, we'll get into a little bit more examples that might be more substantive. I know people are just coming in still, so I'll leave this slide up a little bit longer here. But again, if you want to download it, or if anybody wants to tweet it, I should have actually tweeted this URL. Okay. So I'm going to go through and show how to do the coding here. I'll be doing some live coding during the session. If you want to follow along and you want to do the code, there is a GitHub repo here. Let's see if we get this. So, whoops. It's not in the right mode. We'll leave that one off. There's a GitHub repo there. If you go to github.com/Sateri intro Spark, if you want to just clone that repo, it'll have all the code that we'll be working with today. There's also some small data files that will show the examples for the first part. And then later on in the talk, when I get to the part of doing some machine learning, there's another URL where you can download some data there. It's not very large. Part of what we suggested for the workshop was to go ahead and get Spark downloaded on your laptop. So if you are going to be following along with the coding that I'm doing here, hopefully you've got that downloaded. If not, I'm not sure what the Wi-Fi is like, but it's a pretty large download. But of course, you can do this after the conference too. So first off, I want to give a real quick introduction to what Spark is, if you haven't seen it before. And the setup for this is that in the late 1990s, there was some of the first growth of e-commerce. There was a practice of horizontal scale-out, a lot of web apps that became popular, like eBay and Amazon, Yahoo, Google. They started collecting a lot of data off of people interacting with those web apps, and then they started doing aggregation on the log files and machine learning over the top of what had been aggregated from the log files. And this was being done on clusters of commodity hardware, mostly Linux. So in 2002, 2003 timeframe, Google had built GFS, a distributed file system. And that's really key. Some type of distributed file system is really the underpinnings of this type of technology. On top of GFS, then later on, they published this in 2004, so the work was being done circa 2003. Google put MapReduce on top of their distributed file system, and MapReduce was a way of being able to have fault tolerance. If you had a very large-scale machine learning app and it took thousands of machines, hours to run, if some of those machines failed, which they do, you didn't want to have to restart the job. So MapReduce allowed Google to do these very sophisticated workloads at scale and make sure that once they started, it would complete, as opposed to having to stop it and restart. So that was circa 2002, 2003. We came out with MapReduce. And I want to show this timeline, really looking over a little bit more than a decade. But let's say MapReduce was being done back 2002, 2003. The paper came out in late 2004. By 2006, that was picked up as part of the Nutch project, which is what Lucene came out of, indexing. And they were using MapReduce, an open source implementation of it, to be able to create Lucene indexes for Netch. And so that became called Hadoop. Yahoo started to sponsor that, and I believe they had the first Yahoo Summit, the first Hadoop Summit at Yahoo was 2007. The first one that had a lot of other participation from other companies was 2008. And from there, Hadoop just really took off. So by 2009, if you went to Hadoop Summit, you saw Oracle, you saw IBM, you saw these big enterprise companies coming in. About that time is when Spark started getting developed. In 2009, there was a project, Ben Heinemann at Berkeley was doing a project called Apache Mesos, and some of the other grad students working on the project wanted to look for good implementations that would show how Mesos worked. So one of these grad students was Matej Zaharia, and he used Scala to implement a replacement for MapReduce. He had been an intern at Cloudera, I believe was the story. He'd seen a lot of large-scale Hadoop usage, but he'd also seen where there were bottlenecks. So he wanted to try to resolve some of that, and he did a proof of concept on top of Mesos, and it worked out well. So that was 2009. They came out with Spark. By 2010, they published the initial paper. And then over the next couple of years, this open source project took off. By late 2013, it had become a very popular project. It became top level at Apache, a top level project by 2014. And then coming into 2015, it's become one of the most popular projects in Apache Software Foundation. What I want to show with this timeline is that this happened over a decade. We went from Google doing MapReduce to Spark becoming one of the most popular projects on Apache. And the thing that happened also during this decade was that hardware changed very, very drastically. So, well, and also there was a lot of software issues too. One thing about MapReduce is that it handles batch processing very well, but for other types of processing, not so much. And there's kind of a trend here. You can see where Google will come out with a paper, and then other people will create an open source version of it. So Google had done MapReduce, and then Hadoop came out as the open source version. Pregel was it's an implementation of a type of graph processing at Google. There's the Pregel paper. Apache Giraffe is based off of that, and other types of graph processing. There was the Dremel paper for nested tuples that Google does, and that's now Apache Drill is an open source version of it. There's F1 to Impala. There's Millwheel going to various types of streaming. What this shows is that MapReduce handles the batch, but for other types of processing, there was a number of specialized systems that began to evolve. The specialized systems have a problem because they're complicated, and it takes time and people and money to run a lot of these complex systems. And this was happening around 2009, 2010. A lot of these were emerging. So to be able to build apps that compose not just batch, but also maybe some streaming, maybe some graph, maybe some SQL, it began to be a lot of work. There's a lot of overhead because these require clusters, and there's also a lot of latency introduced when you move large-scale data from one type of framework to another. So for a number of reasons, people were wanting to have a more general type of solution. So Spark came out 2010. Part of it was based off of what was happening differently in hardware. Part of it was because of all these specialized systems emerging. They wanted a more general purpose tool that would cover all of it. Here are two papers referenced by Matej primarily. There was the working set paper and then the RDD, Resilient Distributed Data Set paper. Those were respectively 2010 and 2012. So I want to talk a little bit about the hardware, though. When we look at the kind of problems that Google was trying to solve in 2002, it was mostly because if you have 2,000 machines running in a cluster on spinning disks, you can expect to have a lot of those fail. Even per day, you can have a lot of those fail. So to be able to have fault tolerance on large-scale machine learning apps, they came up with MapReduce. Now, since 2002, the kind of hardware that we have in a data center has really changed. Instead of spinny disks, now we have SSDs, we have multi-core, we have large memory spaces, we have much faster networking. A lot of the fundamentals of what kind of hardware you could expect changed in that decade. And so Spark is really an attempt to take a look at the contemporary hardware, how can we leverage it, and get away from some of the bottlenecks that were introduced by the assumptions of MapReduce. And so Spark, at its core, will go through the API, but up above the Spark core, there's these different types of use cases that are supported. It turns out that SQL can be implemented on top of Spark RDDs pretty directly. So Spark SQL has become one of the main components, the real heavy lifting in Spark. It turns out that streaming also can be implemented using Spark RDDs by having a micro-batch kind of approach, which is similar to what Google does with Millville. It turns out that machine learning can be handled very well by treating your training vectors as RDDs. So again, that maps to the Spark core. And on. Graph processing can be handled. We'll take a look at examples of that later on. So Spark handles a variety of different types of applications, but all over one core. And then it integrates with a number of other systems as well. You can primarily do this in Scala, but also Java is a first-class citizen. There are bindings for Python, for R, or if you want to work just purely in SQL, you can do that as well. And there's plans to support more. And like I say, a pretty rich ecosystem at this point. A lot of different vendors that are actively engaged in integrating with Spark. And if you haven't seen it, just to prove what can be done, about a year ago, in November 2014, Reynolds Shin, who's one of the founders of Databricks, one of the core committers on Apache Spark, they set the world record for something called the Gray Sort Challenge. And it's a 100 terabyte sort. Previously, Yahoo had held the world record using Hadoop, but the Spark team was able to go in and recreate those results, running 3 times faster, using a significantly smaller cluster of machines. So it's about a tenth of the size of the cluster. And across the board, you see this 3 times 10, 30x improvement on most of the metrics. They won the Gray Sort Challenge, they set the world record, but they also went beyond that, and they tried to bump it up an order of magnitude, so they did a petabyte sort as well, just to see. And there's actually pretty good linear scaling across. An interesting thing is that Yahoo, that held the record before, never really published what kind of hardware they were using. They were doing it in a dedicated data center. But the Spark world record was set on top of AWS. And there were really 3 pull requests required to be able to change what was needed for this. And those are public. So if you want to recreate this, you can go out into public cloud and pull down the code to do this. But it shows the kind of flexibility you see with Spark, also the kind of performance gains that you get, again, by removing some of the bottlenecks and taking advantage of large memory spaces, multi-core, better networking, et cetera. OK, so let me shift over here. I'd like to show, well, first off, I mentioned about a GitHub repo, and so that's this right here. So if you go on GitHub under Sateri, that's my account, and go to intro_Spark, we've got all the code and some of the data that's being used. There's actually a video on O'Reilly called Introduction to Apache Spark. And so this is a GitHub repo that supports that video. If you look under source directory, first off, I just want to show right here 00.preflight.scala. And this code here, actually, is this large enough to see in the back? Is that OK? OK, good. So if you want to see here, there's 3 lines of code. And this is probably the simplest program you could write in Spark. So the first line isn't even Spark. It's just some Scala. And it says, create a collection the integers from 1 to 10,000. So we'll create a collection in Scala. The second line says val disdata equals sc.parallelize data. What we're going to do is take that data set in Scala, the integers from 1 to 10,000. We're going to call a special variable called sc. That stands for Spark context. And so that when you're working with Spark, there's always some kind of context that's built in. So we're going to call sc.parallelize, and we're basically going to wrap this data into what's called an RDD, a resilient distributed data set, the quintessential data structure in Spark. And that's the variable disdata. And then the third line, we're going to take that data set, that RDD, and we're going to apply some functional programming here. We say disdata.filter, and then what's the code that's inside of filter is called a closure. Underscore in Scala represents a current piece of data. So we're going to say for each piece of data, filter for the ones that are less than 10. So out of these 10,000 numbers, just grab the first 0 through 9. And then from there, it says .collect. That will basically get the result set. So we're doing a query based on functional programming. We get a result set, and we drop the results down onto the console. So let's try this. Let's see here. Is this large enough to see in the back? Is it good? Okay. So what I'm going to do is I've downloaded Spark, and let's see, env, grep Spark. So I've downloaded Spark. I've got that on my laptop here. And I set an environment variable called Spark Home to point to that directory. So I'll just reference that. I'm inside, right now, I'm inside of that GitHub repo that I had shown before. So to run Spark, I'm going to say Spark Home bin spark-shell. So if I say bin spark shell, this is going to launch what we call a REPL. It's an interactive prompt for Scala to be able to make calls out to Spark. And you'll see there's going to be some log file mentions here. You can also see it shows the version number. So I'm running with Spark 1.5.1, which is the latest release. There's a bunch of warnings as it's setting things up. Those are no problem. Those are expected. And then finally, I get down here a Scala prompt. So I can evaluate any code in Scala. Oh, you know what? Actually, this is being clipped. Let's see here. That's probably a little bit better. Okay. So if I want to say SC, Spark context, is a built-in handle to the Spark context here inside of the REPL. And so if I type SC, it'll evaluate what that variable is. And so it shows us that we've got a Spark context. Let me go back to my example here. Let's take val data equals 1 to 10,000. Okay. So now I've created this collection in Scala of these integers, 1 to 10,000. Let's assume that this is our big data. Actually, it's just a range. It's just a logical description. Okay. And so now I'm going to take that collection, and I'm going to parallelize it to create what's called an RDD, sc.parallelize data, and that's going to return an RDD that we call disdata. And so actually, nothing happened. Other than to create a logical description of it, no processing has been done. We'll go into that a little bit later. But I've got that RDD. So now I'm going to go and do some processing. I'm going to say here, disdata filter for all elements less than 10, and then collect those and drop it back out on the console. And then, boom, you get an array, the numbers from 1 to 9, which is what we expect. So those 3 lines actually show most of the elements for everything we'll do in Spark today. You've got some kind of data source, you create an RDD or data frame over the top of it, and then you apply some type of transformation and some type of a way to actually cause an action that will cause the transformation to be applied and the results to be shown. So those 3 elements will show up in all of the Spark apps that we're going to look at here, and it really speaks to the fact that Spark is relatively simple. Okay. So let's go with a little bit more complicated program to try to show how this operates, what happens on a cluster. So I've got this code here. I'm going to take a log file. Let's say it's a log file from a web app. And the web app is written in PHP, and it uses MySQL, and we've got some errors collected into the logs. Let's assume that the log file is in like log4j kind of format. It's tab-separated values. So the first line here says sc.text file, load a text file. And so I've got where this code's going to live. And then it applies a map. Actually, this is in Python. I should have had it in Scala, but now you'll see some Python used here. It applies a map, and it will take, for each element out of that log file, split it on tabs. So the first line, basically, you get a tuple out of every line in the log file. And that's an RDD. It's called a base RDD. It's basically, it's an endpoint out to where to get the data. So if anything crashes, we always know where to go back and get the data. So that's an RDD called lines. And now the next couple of source code lines there, we're going to apply some transformations. So we'll say lines.filter, and we're just going to look for where the first column equals error. So we're going to peel off the errors out of the log files. And then the next line says, OK, take the second tuple, the second column in the tuple. Since we know that the first column says error, let's find the second column, which actually is the error message. So we're just going to grab the text for the errors, and that's an RDD now called messages. Spark uses something called lazy evaluation, which means that it doesn't actually start to do the processing until some data is required. So as we're building up these definitions here, nothing's going to execute yet. All we're doing is creating a graph of what eventually needs to be calculated. And because we're doing lazy evaluation, as we build this graph, then Spark can go in and make some optimizations on that graph to be able to get a lot better performance. So at the point where we've got messages, nothing has executed yet. We've just built the graph. The next line here says messages.cache. And so that's a directive that tells Spark, the programmer is telling Spark, if you have memory available, keep the messages RDD in memory, if possible. Again, nothing has happened yet. But then the last two lines are where we actually want some data. And you see there that the RDD called messages is being used twice. So this is why we put some caching in, because we're going to use the same data set more than once. So there's no need to recalculate it. When we get to the point of having messages, let's persist that. And what happens there is we're going to say messages.filter. We're going to take a look for the keyword MySQL within the error message. And then we're going to apply a count function. Basically, we're going to count the number of exceptions related to MySQL that are in the log files. And we'll just drop out that count in the console. The second time around, we'll do the same thing, except for we'll look for the number of exceptions that have the keyword PHP in them, and then drop out a count for those. And what this is going to show is how the data is being loaded on a cluster, and then how we leverage memory spaces to be able to get some convenient caching. So when we start out, we've got the application running. Maybe it's on your laptop, you're connecting to a cluster, you're running in the cloud, or you're running the application somewhere on a cluster. But there's always a driver. You're running your application from some point. And that's where your Spark context is. There's also some number of worker nodes. Out in the cluster, there are these resources that are available to do the work. So we've got the driver, and it can talk to the worker nodes. So when we go and start to run the application, again, it's lazy evaluation. We're just building up the graph. All the way up to this line in the code, nothing's happened. It's all on the driver's side. Now, out on the workers, we're going to assume that our data is distributed. Remember, distributed file system is very fundamental here. So we're going to assume that the workers all have local access to partitions of the data. And that's out on disk. Now, when we hit the first action, the count at the end of this line here is actually an action. And that says, go ahead and get the data. So the whole graph up to that point is being evaluated now. When we hit the first action, then this graph gets serialized out to the workers. The driver is going to send the code out to the workers, and then it'll tell them, go ahead, the driver will tell each worker, go ahead and start to execute some tasks out of the graph. The first task is read your data in from your local partition. And then from there, it starts to process, right? We do some filter lines there, we do some maps, et cetera. Each worker has some memory, and it's going to try to persist its slice of the results. It'll save those results in memory in the cache. Now we're asking for a count here, and so the count is based off of a distributed count using partial aggregates. So each worker has its own part of the overall count, and then those are transmitted back to the driver. It sums them together and gives us the results. So that takes care of the first action. Now, when we do the second action, the next line, what's interesting is that we don't have to go back to disk. We've already got messages, RDD, in cache, so we don't have to redo hitting disk. And going out to disk turns out to be very expensive. So that's one of the kinds of optimizations in Spark, is to leverage as much as possible the memory space that you have. Again, working set theory. So when we get to this second line then, because we've persisted messages, it's going to pull messages out of cache and send the results down to the driver. And so when you run this code, what you notice, even with a small bit of data and running it locally, you can see that it's an order of magnitude difference between these two lines, these two actions, because of the caching. And that's a big part of what Spark does. And the thing that's different with Spark versus MapReduce versus Hadoop is that with Hadoop, you've basically got these barriers, synchronization barriers. So when Hadoop starts, applications are split into what are called job steps. Each job step has a map phase, and then sort, shuffle, and then a reduce phase. And so there are synchronization barriers in between these different phases. So you start out, you pull up your data in the map, and you may do some processing on the map, and then it'll go and start to shuffle and sort, and then goes into reduce. So you've got really 3 different synchronization barriers for each job step. And what that means is that your cluster is running kind of in lockstep. You've got to wait for all the maps to finish before all the reduces can finish, of course. And you've got to wait for all the reduces to finish before the whole job step can finish. And that leads to problems if you have a really complex app in Hadoop, because you might have a situation with, say, for instance, like Twitter data. Most people on Twitter have a couple hundred followers. But then you get Lady Gaga and Justin Bieber and Katy Perry and all these celebrities who have 10, 20 million followers. So you can imagine that if Twitter is running through its whole social graph using MapReduce, most people, like us, the job steps are going to run very quickly and finish. But then you hit Lady Gaga, and that particular task is going to be running for hours. So what that means is that your cluster utilization rate overall drops to about 0 because you've got these stragglers hanging on. Spark handles this very differently. Rather than having job steps and synchronization barriers, Spark is using this lazy evaluation. And so it builds up a graph of what needs to be computed, and then it starts to figure out where the barriers actually need to be. It doesn't just have them hard-coded the way that Hadoop does. And it turns out that maybe you're doing map, 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 and then reduce. So rather than being 4 job steps, it only needs to be 1 job step, effectively. So that's why, by leveraging the cache and the lazy evaluation, Spark can get, again, orders of magnitude performance gains over Hadoop. Okay, let me show a couple other examples here, other apps. Everybody here heard of word count before? Everybody, some people heard of word count. Okay, good. Word count is kind of I call it a canary in a coal mine. So with word count, it's a very simple program. I've got some pseudocode up here on the right-hand side. If you do word count in MapReduce, it's maybe 10 lines of code. And it's sort of the hello world for big data. The thing that's interesting about word count is that it's just a small bit of code, but it's got some symbolic processing, it's got some numeric processing. Parts of it are very trivial to parallelize, parts of it are non-trivial to parallelize. So even within a few lines of code, you are exercising a number of properties that you want to have in distributed systems. And as it turns out, word count is very close to some pretty useful work. If you look at algorithms like TF-IDF, it's really just a few steps away from a word count. So TF-IDF is part of the indexing inside of Lucene by default, and other things like that you would see in search. Long story short, if you can do word count efficiently on a cluster in a given framework, you have some guarantees that much more complex algorithms, much more useful work, can also be done efficiently in parallel at scale. So I call it a canary in a coal mine. Word count is interesting on MapReduce, but I want to show a comparison here. If you look at the word count example that ships with Apache Hadoop, it's about 50 lines of Java. If you look at the word count that ships in Spark, it's 3 lines of Scala. And so this has big implications. If you're using functional programming for big data, we really do see a dramatic reduction in the size of the code base. From a software engineering perspective, that's very important. If you have much less code that your team must maintain, you'll probably have less costs over time. Statistically, you'll have less bugs over time. It's easier for people to understand what's really going on in the code if you bring new people in and they have to learn about it. There's a lot of benefits to having smaller code base and functional programming. So let me show here a word count real quick. Word count Scala. So if you go in the GitHub repo and look under 02.wc.scala, I've got some examples here. Let me take this first line. Okay. So what this says is we're going to call sc.textfile, and we're going to grab the README from Apache Spark and use that text file as our data. It'll create a value here, f, that's an RDD that represents the text file. And now to do word count, it's really just this one line. So what we're going to do here is we're going to take f, and we're going to call a flat map. Flat map is much like the map in MapReduce. Flat map says that for one element coming in, you can have 0 or more elements coming out. So what this means is we're going to take, for every line in the text file, we're going to split it on spaces. We're going to split a line of text into a set of keywords. So there's a 1 to 0 or more mapping. And we'll take those keywords and then apply a map to them that says, for each keyword, create a tuple out of it. So take keyword comma 1 as the transformed result. And then from there, we're going to say reduce by key, which says that for each keyword, get all of its values, all the ones, and start adding them together. But an interesting thing here is it says reduce by key. The way that it adds them together is based off of a distributed add, basically a tree structure. And you can get exponential increase in performance by doing this kind of tree structure arithmetic operation. If you're doing more complex operations, you see this very dramatically. This is, again, another way to leverage functional programming, parallel processing in Spark. And an interesting thing here is that this whole line of code is all lazy evaluation. Nothing has actually run yet. All it's done is to create a graph. Okay. And then when we come in here and take the last line, I could save it out as a file, but actually let me just collect it. Boom. So when I say collect, or if I save it out as a file, then the whole graph gets evaluated. Basically, the different partitions of the text file get sent out across the workers, and they go and do the flat map, the map, and reduce by key. So this is a way of parallelizing a count across the cluster. And you see down here at the bottom, the results, you've got keyword, comma, whatever the count is. Basically, you've got this key value pair representation for the results. And the key value pairs are very important. A lot of the data structures based in Spark underneath are really based off of key value pairs. Okay, so let me show another example a little bit further then. Building on that, let's take a look at how joins work. So if we're working in SQL, we've probably got some type of complex queries, a lot of joins. And here's an example of it. I'm going to take some data. Let's see, I can pull this data up. Let me get another one. Source, Riley, Spark. Let me boost this a little bit. Okay, I'm going to look at this data here. I've got data reg. It's on the repo if you want to check it out. But this file here, reg.tsv, here's some data that I'm going to use in my join. And so it's got 1, 2, 3, 4, 5 columns. The first column is a timestamp, so it's got a date. The next column is a UUID, a unique identifier for a user. Say it's a cookie. And then it's got a few other values here. So we're going to take the UUID and use that as our key, and then we're going to use the rest of the data as the value. And we've got another file too, click.tsv. Similarly, we've got this other file here. It's got a timestamp, it's got a UUID, and then some value. So you can imagine that if we take reg and click and join them together based off of the user IDs, then we'll have the values in common. This is a typical thing you would be doing if you're building a marketing funnel and you had registration data and then you had click-through data. For instance, looking at performance of ads, looking at performance of landing pages, things like this. You typically do these large-scale joins to be able to find out ratios in a marketing funnel. So click-through ratio. All right. So if I want to run this query, where am I? Here we go. Back here. So if I want to run this query, then first off, I'm going to go into Scala, and I'm going to define a formatter. And this is just borrowing from Java. It's got a date formatter. So I'll be able to convert the text date into some kind of value. And then I'm going to use, in Scala, there's something called a case class. So for one of the data sets, it's registration data. I'm going to create a case class called register. And then you can see these different fields here. I've got D, which is a date, UID, which is our identifier, and then the additional values, the customer ID, latitude, longitude, et cetera. A case class is a way of overlaying some schema on top of unstructured data. So what we're saying is we're going to bring in some tab-separated data out of a log file, and then we're going to apply the case class over the top of it so that we know what its schema is. So I'll define that for reg, and then I'll also define another one for clicks. So it's got the date, the UID, and the landing page identifier. Okay, and so now let me bring in the registration data. So I want to do a join. So one side of the join is going to be this data set here. I'm going to say load up data/reg.tsv, split it on tabs, and then for each element, I'm going to go and reshape it as a key value pair. I'm going to pull out the first column, the second column, column 1. I'm going to pull that column out that has a UUID. That'll be my identifier. And then the rest of the values are what I want to have as my values in the join. Boom. And then I'll do a similar thing with clicks. So I'm going to load up click.tsv. I'm going to split it on tabs. And then I'm going to reshape the data. Each tuple is now going to be a key value pair, where I've got the user identifier as my key and the rest of the values as my value tuple. Boom. Now, so far, nothing has been calculated on the cluster. This is all just definitions building out a graph of what eventually needs to execute. So to perform the join, really all I have to do is here, I'll take the first RDD, reg, and say .join to the next RDD. Since both of these have been reshaped as key value pairs and they have keys in common, it's trivial to do a join on them now, or it's simple to do a join, I should say. It could be very large data, so it's not trivial. But reg join click, and then I'll say collect, and now the graph will be evaluated. Boom. And so you can see here, the result that you get back is a key value pair. And so you've got the UID as the keys, and then the left-hand side and the right-hand side, registration and clicks for the values. So that's how joins work, and there's a richness to this. I'm showing a very simple type of join. There's a lot of these that are implemented. Realistically, you probably never do this level of programming, but I want to show how it works. And the reason is, over here, that when we're running SQL in Spark, and we're doing some complex queries, some complex joins, this is what's happening under the hood. This is the parallel processing out on the cluster. When I was doing the transformations on the registration data, let's call that stage 1. So I load up some data, I do some maps on it, I reshape it. And that's one unit of processing that can be done in parallel. When I do the stage 2 is where I take the click data and I reshape that. That can also be done in parallel. Now, when I get down to the last line and I want to join the left-hand side and the right-hand side together, now I have to have a synchronization barrier. I have to take and compare all the elements for each key. And they could be distributed across the cluster. So you can see there's going to be some network traffic as I'm doing this join. But up until that point of doing the join, the two sides of the graph can be run in parallel. And so that shows what Spark is doing underneath to optimize is to take this graph and figure out which parts can be run in parallel, which parts can be run as a single unit of work. It does that optimization, but then when it needs to have some kind of barrier, like on the join, that's when you can get an expensive operation. Now, a way to get away from this being too expensive is you could repartition data, move it around so that all of the values for a given key are located on the same server as much as possible. And if you were to do that, then a large-scale join would be very, very simple to execute. OK, clear as mud? Is this making sense? OK. I can barely see up there, but it looks good. All right, so those are some of the essentials of what's going on with Spark at a low level. I'd like to show a little bit about diving into the API, the core API, showing what the different elements are before we go in and actually get to some of the other coding. So first off, in a Spark program, you're always working with a Spark context. There's going to be some variable around, probably called SC. This is available if you're working in the REPL or if you're working in a notebook. If you write a standalone app to run Spark, one of the first things you'll do is to create a Spark context variable. If you start working in Spark SQL, then you've got a wrapper on this, and now you've got a SQL context. Streaming has a streaming context, et cetera, et cetera. But they've got this Spark context at the base. Inside the Spark context, you've got some different parameters. One of them is called master, and it always points to where the cluster is. In this case, I'm running off my laptop, so the master is just local. I'm just running on my local machine, but if I wanted to, I could redirect that out to some cluster running in the cloud. That could be running on Yarn, Mesos, Spark Standalone, et cetera. And so the way that this looks when you're running applications is you've got the Spark context on your driver. That's where your application starts. The driver is going to be talking with the cluster manager. The cluster manager goes out and gets resources from the cluster, maybe some different worker nodes. And then the driver can talk to those nodes directly. Each worker node is running a process called an executor, and that's really what does the work. The executor is responsible for understanding where the data is cached. It's responsible for taking and executing the different tasks. If a worker node dies, that partition of data and those tasks can be taken up by some other worker node, some neighbor. So there's a lot of fault tolerance as well as the parallelism. Now, again, at the base of this is something called an RDD, Resilient Distributed Data Set. So it's like having a collection in Scala or any other language that has interesting collections. And you can apply functions to those collections. That's how you build up the graph that needs to execute in Spark. And that's really most of what's going on underneath Spark. There's a couple of ways to build RDDs. One is, as we saw, we could take data that we've defined as a Scala collection and then just parallelize it. Or we could take external data, some sort of data set on a disk, and bring that in. There's a number of ways that you can bring in data. It could be coming in as tab-separated values. It could be coming in as Parquet or sequence files, JSON, et cetera, et cetera. Now, there are two kinds of operations that are in the API, two types of things that you can do to an RDD. One is you can apply a transformation. The other is you can apply an action. The transformations are lazy. Transformations are not calculated right away. They just build up the graph. The actions are when the graph gets evaluated. So you do transformation, 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 and you hit an action, and the whole thing triggers. The other thing you can do with an RDD is to persist it. So there's a few different levels of persistence where you're caching them. We'll talk about those in a little more detail. So we've seen how to create an RDD. The transformations are lazy. The lazy evaluation allows us to do some optimization, and it also allows a way to recover in case one of the nodes crashes. It's a very convenient way to be able to handle the fault tolerance. So it gives us both parallelism as well as fault tolerance. Now, in terms of transformations, here's a few of them. We've seen a map, we've seen a filter, we've seen a flat map. You can sample. You can take two RDDs and union them together. You can do a distinct to get the unique elements out. It's very similar to some of the things you'd see in SQL queries. If you have a key-value pair as an RDD, then there are other types of transformations. You can do reduce by key, which is what we saw in the word count. Similar to reduce by key, there's something called group by key. But group by key is probably not what it sounds like. And in fact, most of the times you don't want to use group by key. It breaks some of the parallelism. There are reasons for using it, but just keep in mind, reduce by key is probably what you want. There's a number of these. I'm just showing a few of them, but there's sort by key, a lot of different things you can do on key-value pairs. Join was one of the things. Underneath join, actually a superset of that is a co-group. You can take and do a Cartesian product on two key-value pair RDDs, et cetera. These are all transformations. Actions are when the lazy evaluation gets triggered, the graph gets evaluated, and things run out on the cluster. So some types of actions here. We've seen using collect, so that's where you evaluate the graph and drop the results out. We've seen using count, and I think I had an example there of take. Take is a way of like a limit in SQL. It's a way of just getting a few elements out. You could do take sample. You could do first, which is a take one. You can also do reduce, which is an action that will take some type of function and apply it to the graph. What's interesting is that reduce has some mathematical properties. It requires the functions to be commutative and associative. So this is where we start to use some abstract algebra to be able to get great efficiencies in parallel processing. The other thing that actions do typically is working with I/O. So if you have a terabyte of data coming out of your Spark app, you don't want to drop it on the console. That'll throw a memory exception. So instead, typically, you're doing some type of save in parallel out on the cluster. So save as text file, save as JSON, save as Parquet, et cetera, et cetera. You can also do things like count by key. For each is a way of applying a function out across all the partitions and then dropping the results back. There's a number of these types of actions you can use. I mentioned the other thing you can do with RDDs is persistence. You can define how a data set will be persisted in memory or disk or wherever. So there's a few different options. By default, you're doing persistence with memory only. So when I use the cache function, that's persist memory only, and that says store the RDD as a deserialized Java object in the JVM. If parts do not fit in memory, then if you need them again, you'll have to recalculate them. So if you're doing just very simple maps on your data, it's probably more efficient to actually recalculate than to store them. So the recalculation is an interesting trade-off if you do have large memory spaces and multi-core. Alternatively, you could do memory and disk. And this says, store the RDD as a deserialized Java object. If it doesn't fit in memory, store the parts that don't fit on local disk. That's a lot like spilling to disk if you're using Hadoop. So now instead of recomputing, you actually store some things on disk. If you've got a really complex graph and you're maybe doing some machine learning or something that's very expensive, you probably don't want to do the recalculate. Instead, if you need it, you want to grab it off local disk. There's a number of different variations on this. You can do disk only, basically turning the memory off. When they did the world record gray sort, they actually used disk only. They didn't use all the memory features. They could have done more, but they wanted to give a fair comparison with Hadoop. There's other varieties as well. Two other things. There's something called a broadcast variable, and this is not an RDD. This is one example of where you've got data in Spark that's not an RDD. So a broadcast variable says, take some data set and make a read-only copy of it and send it out to all the workers in the cluster. That's a good thing to do if you've got maybe an anti-fraud model, some kind of machine learning model that you're wanting to send out. It could be that some algorithms need to have global state, so broadcast variables can be used there. There's another thing called an accumulator, which says I want to take and apply some type of function, and maybe I'm accumulating a value. I've got some kind of measure, or I'm accumulating a set. So for instance, when you're running a lot of parallel processing, if there's exceptional data, you may want to accumulate what those customer record IDs are and report them afterwards. Or you may be using accumulators to measure some of the resource use inside of your algorithm. A lot of different ways you want to do an accumulator. The one thing about it, though, is they cannot be read on the worker. They can only be read on the driver, because accumulators are distributed by nature. No one worker would be able to see all the data. All right. So let me go through a little bit of Spark SQL and describe how this works, and I'll show some examples of it. There was something called Shark, which was a way of taking Hive, and instead of having Hive be based on Hadoop, the back end of it was based on Spark. And for a lot of queries, benchmarks that we were running, about 100x performance by replacing Hadoop with Spark. But they got to a point where they recognized that the optimizer in Hive wasn't really robust enough. They wanted a better optimizer. So they came up with something new called Spark SQL, and then they started doing a lot of work on optimization. Here's a pretty good talk recently from Michael Armbrust, who's the lead on Spark SQL. It's one of the newer parts of the Spark core API, but it's become one of the most central parts of Spark. And I'll definitely point you toward documentation. There's a lot of good docs that describe sort of the theory of Spark. If you want to go into more detail about setting up SQL, I'll show some examples of this in a bit. Let's see. Oh, wait, we're 13:30, so we're past time, aren't we?
Yes, I did.
Oh, man, OK, sorry, I didn't even see the time. OK, wow. Well, OK, here's the thing.
As you mentioned before, if anybody would like to ask Paco any questions, he's more than happy to help out during the any break that we have. Unfortunately,
yeah.
I didn't want to interrupt, but we're running very late.
Sorry.
We cannot actually do the lunch break now, the short break now. We have to go straight into the talk reducers because unfortunately there are 15 minutes, and otherwise we're just not going to have everybody fitting in. So deep apologies, Paco, and I hope
No, sorry, yeah, I ran out of time. I'll be outside. The code is all online here if you want to work through some of the exercises. We've also got a video that describes a lot of this if you want to check out on O'Reilly. Thank you very much.
Thank you.